So saying I'm originally from Trinidad and Tobago in the Caribbean. And I have to tell you that because everyone tells me that they missed the first part of my talk trying to guess where I'm from. So now that I've solved that question for you, oh, great. Now that I've solved that mystery, I guess I have everyone's full attention. Okay, so this is joint work with a lot of other people. And I'm a research scientist in a group at Harvard that focuses on producing online courses. So what I find very compelling about explanation is that it's a complex enough phenomena that it has real-world impact in settings like education. And people have extensively studied how students explain helps them learn. On the other hand, it's tractable enough that we can get some pretty generalizable insights into it from the perspective of psychology, as many people in this room have shown. But even though my dissertation with Tanya ostensibly took this approach, taking educational phenomenon and understanding it from the perspective of philosophy, subsumptive constraints, and running lab experiments, I do feel like it didn't quite hit the right point of productive integration. At a theoretical level, when we look at education research papers, they often talk about explanation as any kind of activity that's articulating out loud. It might be explaining the meaning. And that doesn't quite line up with the way we often operationalize explanation in psychology. For example, distinction between explaining why and explaining how. So how could we get some more productive integration where we're able to map these concepts together, very much in the spirit of Andrew Simpian's and Frank Kyle's PBR special issue, where we're using the same kinds of materials? So the approach that I found to work very well is actually to take advantage of digital education. So this really simple step from students doing their homework on a piece of paper to now going online and solving, let's say, math problems on a computer. It's actually can be a pretty unprecedented opportunity because I see anything that's digital or online as basically bringing together the lab and a real-world setting. Because there's students right now who are doing homework online. And those are vehicles where we can do randomized experiments where we've got control, where we can collect data on a large scale, and we can really operationalize concepts in a precise way that we can replicate and investigate them. So I see this as a potential avenue to sort of align the interests of researchers like many of us with actual practical impact. Can we do these experiments in vivo, in the real world? So I'm going to talk about one paradigm I found particularly fruitful for my attempts to run these experiments in the real world, online math problems. I'm then going to talk about actually all the obstacles that come up when you try to do this. And one approach that I've developed with collaborators that I think helps to better align teachers and scientists so that we're both getting what we want. I may talk about one application of this approach to a system. And I think I'll close on really what I think is probably of most interest to you. How can you use the kind of technology framework we've developed, which we call MOOClets, to actually conduct your experiments in these settings? So here's one paradigm that I use when I've conducted experiments on Khan Academy. It's an online math website. You might think about a student who solves a problem. They get asked to answer this question, and they've got to type an answer like, what's the expression? Or how do you differentiate 3x plus 59x squared? So they type an answer, and then they get feedback. Well, actually, here's the correct answer. And at this point, you can start thinking, what are the things that you might manipulate that are going to be practical, but also let you test some interesting hypotheses? Well, one that I and Tanya and many other people have looked at is one that, for example, has been from education is providing explanations. So what kinds of explanations we provide students about why that's the right answer? And another is, of course, prompting people to explain, which I and Tanya and many other people have looked at. And this mirrors what Claire pointed out earlier today. You can think about investigating what explanation is useful and also prompting people to explain. So there's a wide range of experiments you can run in this context. I'm not going to talk about those experiments, but actually the kind of barriers that have come up in trying to run these, and why I think they need this approach of collaborative dynamic experimentation. If you sort of walk away with that, understand that, I think that would be the most useful thing. So here's a problem. When we're trying to bring together teachers and psychologists, I've run experiments where teachers felt that it wasn't necessarily helping their students. It just didn't test things they found interesting. And then in other cases, I've had to run experiments where I felt like I wasn't able to get a scientifically interesting question. I was just replicating past work. So the kind of challenge here is, how do we align these set of questions that teachers want to answer with set of questions that psychologists want to know that's really pushing a theory forward? Let me try and decompose that problem a bit into thinking, well, what are experimental conditions that teachers might want to compare? And here, when I say experimental conditions, I'm thinking of things like different explanations for an answer in this kind of paradigm, or different kinds of prompts you might want to give test out. So how might we think about what is the set of experimental conditions teachers want to compare, whether they be different explanations, different explanation prompts? And the set of explanation prompts or explanations scientists would like to compare. And the ideal thing is to, as much as we can, get to that intersection. Even if we can't, though, one of the advantages of online experiments, for example, one that we ran on Khan Academy, it was a 3x4 x 5x2 design with about 2,000 people. We can be a bit democratic here. Karen can say, here are my 3 conditions, and Claire or someone else can say, here are the 4 that McGraw-Hill wants to run. And you run all of these together. So I think that it's a very simple kind of idea, but this idea that we can use experiments as already a vehicle for getting people to collaborate and actually coordinate in this way, I found has been very productive. And it's why the early experiments that weren't so informative have now transformed the later ones that are. Here's another kind of problem, though. A lot of teachers or others wonder, when is it ever ethical to run an experiment? Why am I providing students in a class with different experiences? So when is this fair? Well, let's think about the teacher's perspective. I want to think about what's best and give that to 100% of people. And I want to, if I have 2 explanations, I think this one's better, so I'm going to give it to 100% of people. I'm giving 0% of people the other. So in my opinion, they're running an experiment. There's just 0% of people in the control condition. The scientists would say 50%, 50%. That's just how we're going to do it. Is there any kind of compromises in between these? Well, you can think about something like actually assigning people to conditions, the probability of assignment being weighted random instead of uniform random. So now what I found has been very effective with teachers is saying, well, how sure are you that this condition is better than that? Well, in proportion to your belief, I'm going to assign people. So if you're totally sure, then it's just 90% versus 10%. If you're middling sure, then it's more like 52% versus 48%. And so it's not typical, and there are good statistical reasons for that. You tend to lose power when you use weighted randomization. But if you think about the amount of power you lose from 100% to 0 to going to 90 to 10, you can see that's very preferable for scientists. And I think it's also really been powerful for sort of getting experimentation into practical settings. So that's nice. That kind of helps push a bit on the ethics of this. But here's another issue that comes up. Well, when do I stop running experiments and actually just give people what's better? How do I actually improve my online math problem? And again, we can be very bold. Let's just stop after Y students. 100, we're done, the experiment's out, everyone gets a better version. Or the researcher can say, let's never stop. Let's wait until the entire experiment's done, everyone's gone home, and then we're going to analyze the data. You might guess what I'm going to suggest next. How can you actually interpolate between that? And so here's an interesting idea. What if you actually, instead of going from 100, instead of going 50-50 and then bam, stopping at 100-0 after 100 students, versus 50-50 all the way, you could actually think about dynamically modifying the probability of random assignment after every student. And so this is a kind of funny idea, and I'm sure in your gut reaction, you feel the way I felt when I was first started to think about this. That has to be wrong. Well, actually, there's extensive literature in the medical field, adaptive clinical trials, and also in actually computer science and machine learning, which has been used a lot in things like website testing. And they basically have a lot of very effective algorithms and statistical methods for dealing with these kinds of issues. And so the kind of key idea here is that if you were running an experiment, you might start off, let's say, 50-50. But as you're accumulating data that one condition seems to be better, well, maybe you change it to 50-48. Then it's 60-40. Well, actually, you realize that that was just an illusion. It actually looks like it goes the other way. Now it's back down to 50-50. Then it's 30-70, 20-80. So the idea here is that there are methods for actually smoothly varying how many people are assigned to a condition. And the nice thing about this is it's, again, trying to balance the teacher's need for an ethical experiment that's actually helping people with actually scientists' need for saying, well, I need to be able to draw reliable statistical inferences from this data. And in fact, one thing that's nice about these methods is that as much as your gut reaction might be that there's something weird going on, there's something funky, there's specific literature on under what conditions this is reasonable and under what conditions it isn't. And so I presented some of this work at a statistics conference, the Atlantic Causal Inference Conference, and actually statisticians were much more comfortable in this than the average psychologist. And I'm happy to discuss the conditions under which this is or isn't a reasonable thing to do and what you have to watch out for. Thank you. So at this point, I would actually be happy to stop. I basically tried to introduce this general idea and say we could basically start using these digital resources to run experiments in online settings. I introduced some issues that come up. How do we get alignment with teachers and scientists so we can collaboratively design experiments? But also, how do we start to tackle some of these ethics, issues with ethics? And these are the kind of arguments that can be approached. I'm going to briefly touch on one system we built that didn't realize the full goal. I just see the setting the stage, but I can't resist showing at least some kind of data. So this contribution is not a psychological contribution. This is published at a human interaction, an education conference for learning at scale. But the key idea was, let's take one of these math problems and let's actually build it so that we can at least get some version of this kind of collaborative dynamic experimentation. So in this case, and it's called AXIS, Adaptive Exclamation Improvement System. That's how HTI and people like to sort of write things. The key idea here was that we took some materials from, like what's used on Khan Academy. In fact, I work a lot with a platform called Assessments, and that's where any of you could run experiments if you're interested. We took that math problem. After students saw what was correct, they would then be given an explanation for like why that's the correct answer. And that was randomly assigned from a pool of explanations. Now, where does that pool come from? Well, it's actually, they would also be then asked to rate how helpful the explanation was. So the idea is we could try and adapt the probability of receiving an explanation based on something like whether someone gets the next problem correct. And that's what I tried to do at first. That was actually less reliable than asking students to rate explanations. So as leery as I felt about using a subjective judgment, that's actually what we found gave us better results. And I'll tell you later how we objectively assess learning. So that's the kind of paradigm. You get an answer, you get given an explanation, you rate it. And that's what we can use to adapt the experiment. But now, where do we get these explanations from? Well, I deferred in this case to the practitioners. They wanted to test whether we could actually get them from students. So we actually then asked students to explain, why is this answer correct? So they actually had to generate this explanation. And if they thought that would be helpful to others, then that was added into the pool. So you can kind of see the system here. We're getting the pool of explanations from students, and then we're randomizing. And we're going to try and dynamically optimize based on people's ratings. OK, so I'm going to go through this super quick, but I'm happy to come back to it later. Basically, we just recruited 150 participants for online for Mechanical Turk, and we're running the student version of this in Assessments. There were 4 algebra and probability problems they had that they were prompted to explain for and get explanations. And we ran a dynamic experimentation algorithm after every single participant rated an explanation. So you've got your pool, and every time someone rates an explanation, we change the probability of the next participant getting that explanation in proportion to whether that explanation is rated higher or lower than the others. Now, we ran that on 150 people, so we end up with a pool of explanations and a probability distribution over them. Then we ran a separate study where we compared the output of the system to no explanations at all and to explanations written by the instructor. And there we actually include a pre-post test measure of whether people learned. So I don't expect anyone to follow that, just for the computational modeling people. But we use a particular algorithm called Thompson sampling out of the multi-arm banded literature. And as I said, the key intuition behind Thompson sampling is that the probability of someone receiving an explanation is the probability based on your particular model that that's the best explanation out of the entire pool. So at the end of this, you get a probability distribution over explanations, as I mentioned. So now in our separate experiment with 564 people, we're randomly assigning people without anything adaptive to receive either no explanation, explanations from the system, or instructor explanations. We actually found that explanation system did actually significantly increase accuracy in solving problems. How much worse are these than the instructors? Because maybe just any explanation helps. Well, actually, they were comparable to the accuracy of the instructor. So the explanations the instructor had written were just as good as these. They didn't differ significantly. OK, so just to kind of close then, this term MOOClet refers to a technology framework. And this slide is really for all of you. Part of what I do now is design technology that I use, but also that people like psychologists can use. So MOOC, it comes into a massive open online course, and a MOOClet is just a technology to enable collaborative dynamic experiments. So if you wanted to run this in a platform, how would you know if you could? The technical issues, the political. Well, the key idea here is that if we take a paradigm like this one, we implement pieces of these as MOOClets, so that if the explanation is a MOOClet, like in the system, then you can propose experiments and get data back in real time. If the prompt is a MOOClet, then that's actually what you can pose your experiments based on. And Neil Hefner and I, Neil runs the Sysmonths, he's a Worcester Polytechnic. We have an ongoing NSF grant that actually enable the technology that external researchers can just go into Sysmonths in these kind of paradigms and propose experiments, which then actually would be deployed into classrooms. And we actually have a pending NSF Scientific Learning Collaborative Network grant, which hopefully would actually enable these kinds of collaborative experiments between teachers, psychologists, and education researchers. So the key question is really, are there ways in which this would be of interest? And probably not now, but in the next years, as you think through these kind of theoretical issues, how would they intersect with these kind of practical contexts? And feel free to drop me an email if you're interested in collaborating on that. Jeff has actually been working with me on running experiments in MOOCs on testing some of his work, and Steve Stolman's on complexity of explanations. And in fact, the course team we worked with did not insist you use this dynamic experimentation. So Jeff's just got away scot-free. One thing that I want to close on that I'm really excited about is, one thing I've started doing is thinking, well, when we're running these experiments, MOOClets are also designed to enable you to start experimenting and then actually discover how to personalize. So if you think about it, when we're experimenting, we might give people an explanation or another explanation based on variables set randomly. But suppose we actually discover treatment-subject interactions. Like, this explanation is better for low or high knowledge. Or this explanation is better for this kind of problem versus that. Well, actually using these machine learning algorithms, we can actually start off experimenting and then just flick a switch without changing anything and start personalizing. So we start delivering explanations in a personalized way to the people who are going to learn most or benefit most from those. All right, so thanks so much for your attention. Yeah, sure.
I think this is all very interesting. I actually had a different ethical question in my mind. The time that I allocated students during assessments, and typically assessments carry weight to them, right? Otherwise, either they unlikely do them at all or they don't do them with attention. So if I graded